Good morning and welcome back to the lecture. So, we will continue where we have stopped. We have introduced the Green's function in general and that we have derived the Green's representation formula if there is a solution. So, let me start with some comments. We want to solve this problem. Our aim is to solve this problem, study the existence in omega. So, you will see how difficult even that such a simple operator on d omega. Of course, we are not going to do this in this course at all completely in the generality. So, let me complete what am I going to do it. Okay. So, this solution you can write it as u equal to v plus w, and then what is v? V is Laplacian of v is equal to f. So, separating your internal source and term and then external. By linearity you can do it, and minus Laplacian of w equal to 0 in omega and w equal to g on d omega. This is done with the linearity. So, we will do this one. So, what are we going to do? We are not going to do this problem. This is part of PDE 2, existent part of PDE 2. We will study that. Okay. And this is called what is called the Newtonian potential. Newtonian potential. And you need to introduce what are called Hilder continuous functions. We will do it in the PDU 2 course. Hilder continuity, all this we will do it in the part 2 for you. That is the main part remains which we will do it in the thing. For this case also general case in PDU 2, general case, general domain I mean in PDE 2, that is we prove the existence what is called Perron's method. Perron's, you have to introduce more general super and sub solutions, and there are some difficulties. You have to introduce the regularity of the domain and all that. But what we do it now in the remaining lectures of elliptic this Poisson equation, we prove existence, we prove now, we prove existence when omega the upper half space that is equal to R n plus. What is R n plus? Set of all x1 etc. x n, which we also write it as x prime x1 x n. Okay. For the convenience where x n is positive. Okay. That is your R n plus, that is upper half plane, and we also prove this is a case 1 omega, and 2 you prove an omega is a ball of radius r centered at x naught. So, these two cases we are going to prove it in the existence theorems. Okay. All right. So, that is what our plan now. So, we will introduce the Green's function for Green's function for R n plus. So, R n plus is in 2 dimension, you can precisely write it, right. This open set, this is R n plus, this is your R n plus, this is your boundary of R n plus. Keep all this in mind. R n plus, you can view it as a R n minus 1 you can view whatever way you like it, or you can view it as x prime 0. So, these are all identifications with x prime in Rn minus 1. Okay, sorry, the last, that's okay. Okay, so and its normal derivative is this one, you see, the normal nu is equal to 0 etc. minus 1. You need all this to compute on the boundary. Okay. With all that, we use so you want to introduce, so you already have phi x minus y. Let me recall the Green's function g x minus y is equal to minus phi x of y. Okay. So, you want to find this should be harmonic. So, we use symmetry, of Rn plus. Okay. So, if you take a point here, so let me extend it. So, if you take a point x prime x n here, so you look at its symmetric point here, this will be x prime minus x n, and when you come here it will be x prime 0, x n comes to 0. So, you take your same phi, so this is your x if you have it, and I call this to be x tilde. So, if we take, so this is symmetry if I am using, if I use phi of x y, so y is on the x and y are different, okay, g x y is different with x and y. If I take x here and if I take phi of x minus y, and if I consider this domain upper half plane, in the upper half plane it has a singularity, but if I use x tilde as my singularity, in the upper half plane it will be. So, look at here this function phi x minus y tilde x tilde minus y. So, you have to use that one, okay, y minus x tilde, both are fine. So, if I use x tilde minus y satisfies the singularity is at y equal to singularity we are treating it as a function of y, singularity at y equal to x tilde. That implies immediately Laplacian with respect to y phi of x tilde minus y, whether you use x tilde minus y or y minus x tilde, or all that does not matter, because phi is modulus, so it is defined in terms of the modulus. So, it is fine. This is equal to 0 in Rn plus. So, you immediately got a, the only problem which you have to verify. So, this is a small exercise for you to verify. Exercise, you want to satisfy the condition when y is on the boundary. If y is on, x is internal, x tilde is internal, okay. If y is in the boundary, show that this trivial, just write down, that is all, but it is better for the first time if you are learning, is better to do it one. Then phi of, you have to careful, x tilde is the thing, y, the yn term is 0, this will be same as phi of x minus 1. Okay. So, you have your already, so just use the symmetry to do this. So, this implies your Green's function for the upper half plane is equal to phi into x minus y minus phi of x tilde minus y, where x tilde is the reflection point. So, you see Green's function okay, for Rn plus 1, that is what. So, you have immediately your Green's function. So, this implies immediately you can write down the Green's formula. So, your ux, so if u Yes. So, let me before that let me so I am only going to study this problem. So, we only study I told you what we are going to we only study in this course minus Laplace and u equal to 0 in omega and u equal to 0 g. This is the problem which we are going to study when only two cases when omega equal to r n plus or br of x. So, first we are considering r n plus. So, you have a so in r n plus. So, you first do it r n plus and for br of x naught we will do it in the next class. So, we will give more details here. The similar things can be computed by the students when they study. In r n plus the Green's function g x y is already done. Okay, we are repeating actually, but let me do it because minus phi x tilde minus y we already done, is not necessary. So, if you solves one, so I call this to be 1, solves 1 with omega equal to r n plus, we are doing it, then the solves smoothly, then u x equal to, this is the Green's formula, integral g of x y is this one. You have to compute that one. Okay, you have to do all that g of x y. That term won't come, f is 0 because f we are not considering. So, we do not have anything. So, u of x y is equal to f is 0 in this case, that is what we are studying. The other thing is more thing. This is in boundary of r n plus dg by d nu y, and now you know how to compute d nu because it is d phi, both are d phi, only thing you have to take the normal correctly. So, you compute the normal derivative. So, I will leave that as an exercise g of y ds y. I am giving a more computations. Okay. So, you have this. So, your job is to compute. So, I want you to compute. So, I leave it as this is exercise which we are keep on doing it. Now, we are doing it compute dg by d nu y. Okay. When you compute that, so I will do the computation result. You know this is already equal to dg by dy n, right, because the normal here is 0 etcetera 0 minus 1. So, d by d nu the derivative will be minus d by dy n, the nth derivative. So, it is easy to do that one. So, you compute this and you get what you get here is, this is an important formula which you know, minus 2 x n by n omega n mod x minus y power n. Okay. So, this is important. So, keep this formula in your mind. Okay. So, you can precisely calculate your dg by d nu. Therefore, thus u x equal to the formula, if you solve u x equal to, so let me, so thus exactly what u x, if u x solves this equation 1, then if you thus u x equal to 2 x n. So, you have a minus sign there, 2 x n, there is a minus sign, yeah, there is a minus sign here, I did write that. Okay. So, that minus minus get cancelled, you will have n omega n integral of g of y y mod x minus y. This is on the boundary, so x n can take it out. Yeah, that is why it is coming. This is in R n minus 1. Okay. So, x n won't come into picture. D R n plus. So, d s y, keep that in this case your d s y is nothing but d y prime, keep that in mind, okay, because it is in this R n minus 1 direction. So, your d s y is same Levick measure because it is already flattened domain. So, this is, so you can easily integrate. So, you have your formula, but let me use a notation d s y because you can't do it this all the time d y prime. Okay. So, we introduce what is called the Poisson kernel, therefore, definition Poisson kernel we introduce k x y is equal to 2 minus 2 x n whatever it is 2 x n. I am using write down everything for this case, later you will see x minus y power n. This is your Poisson kernel, that is therefore your u x is a compact notation I am giving, integral of k of x y g of y with a kernel integral form. So, you see this is very important to understand, right. Getting an integral formula is precisely when you have a function, even these are all kind of more generalizations, right. When you have a derivative and if you want to solve the inverse problem g by dx equal to f, you write g is equal to integral. Similarly, you solve a second order operator Laplacian, then you are trying to write u in an integral form, that is what. So, to see that these are all kind of fundamental results, right. If you have one dimension, if you want to solve dg by dx equal to f, how do you write? Then integration theory is developed and you write g is equal to integral of f of x dx, right. Here you have an operator L which is Laplacian in this case, and you have Laplacian of u equal to something including the boundary condition. So, you are trying to invert that operator Laplacian, in some sense you are writing your minus Laplacian inverse. Can it write that minus Laplacian of inverse, can it have an integral representation? And what these results tells you is that you can indeed do that, but not as simple, but with the kernel k. Okay. That is the importance of this. You have to see all that result in that context, in that generalization of all that, all right. So, these are all general comments. So, you have this kernel and then this is called the Poisson formula, Poisson formula for upper half plane. Okay. This is also Poisson kernel for R n plus, everything in that, and then this is Poisson formula for upper half plane. But as I said, this you are getting assuming that u is a solution, but now we want to prove that this u is indeed a solution, whether this integral is meaningful and does this solve everything. So, let me try to do that one and state a theorem maybe in this thing and try to prove that theorem in the next class. If we get time, we will do here. Observe now. So, kernel. So, you can prove some results which I will not prove everything, but I would like first timers would like you to do these things. So, I will leave it as some exercises here. Okay. It may be some computations, but first time you do it. One, yeah, before that you will say that if y is in R n plus on the boundary. So, before the exercise let me have this comment. If y is in R n plus, so you see here y, the singularity of k is when x equal to y. If x is here, x minus, so you y is on the thing, k has no singularity, k x y has no singularity for x in Rn plus. It is in the upper half plane, that is open set. Okay. That is fine. In fact, k is C infinity. Okay. So, for each x, so you can see that k is a C infinity function, which is I think for y in Rn, k is a C infinity function, k is C infinity. Okay. So, there is no singularity at all here. So, the exercises which you can prove with that notion, Laplacian of x of k x y, k dot of y, y is on the boundary, that in fact this you can prove it 0 for it is x not equal to y, not even have to be boundary. Why I say that when y is on the boundary, there is no singularity for x in inside. You have to understand how these singularities behaves. Okay. So, you because k is coming exactly from the Green's function, and Green's function coming from the fundamental solution. So, all these are things. What the second thing which you may need to do some work, if you integrate this one on the boundary Rn plus, you integrate k of x y dsy, that is equal to 1 for all x. You see. So, you have the same thing. It is very crucial to prove this. All these will be used. And another thing which you have to understand, since k is C infinity. So, if k is C infinity, so let me not write that is k is C infinity for y in Rn, y on the boundary. Yeah, understand this kernel very nicely. K is C infinity, and assuming G is bounded, G is a continuous. So, assuming say G is continuous and bounded, you can actually show that u is differentiable. So, these things together tells you can take differentiation inside. So, you can compute will give you can take as differentiation inside. So, because it is C infinity, and you can do this integral over boundary of Rn plus d power alpha x of k, you see, k of x y g of y ds phi. So, there is no problem in taking inside the integral. Okay, with all this smoothness and all this boundedness, you can. In particular, Laplacian of u equal to 0. That is what it shows, right? Laplacian of u equal to 0 in Rn plus. This is what you want to solve it. So, only this boundary condition you have to solve it. So, one part we already got of the solution, you see. So, this is in Rn plus. So, that immediately you take alpha d square u by dxi square and do that, alpha equal to 1 0 0 and sum of it, you get Laplacian k, because Laplacian of u inside you get Laplacian. So, there is no problem of taking the Laplacian there, since k is infinity and you are working with the boundary. So, you can prove all these things. So, you have your Laplace. So, the first part of the result is proved. So, what you have done, so that implies the following theorem. We will start the proof, maybe we will continue in the thing. So, I will try to give the idea. So, let me write the theorem, maybe proof I may not be able to compute. So, I will stating. So, assume G is in CB of Rn minus 1, right. Rn minus 1, this means it is bounded. Okay. So, you have a bounded continuous function. So, this is the space of bounded continuous functions, space of bounded continuous functions. Okay. Okay. Then you define, defined by the Poisson formula, defined by, or rather given by, you given by Poisson formula satisfies one u is also a bounded continuous function, which we already seen essentially. Okay, so let me not do that, you can do that. 2 Laplacian of u equal to 0 in Rn plus, and what we have not proved. So, this is proved, this is done, and what we remains to prove, it satisfies the boundary condition in the sense of limit. You have to understand, because you boundary you have to understand, and G is just continuity. Okay, so you are not writing G, because u is defined only on the interior, u is not defined on the boundary. So, you have to be careful. Okay, the Poisson formula defines u in the interior, in the Rn plus, not on the boundary. So, how do you interpret the boundary value? So, to interpret the boundary value of u as a limit going to 0, and that is what we need to prove it. Limit of x tends to x naught, where x naught equal to of u of x is equal to g x naught for all x naught in Rn, boundary of Rn plus. Okay. So, what remains to prove is only remains to prove this fact, remains to prove. So, you have one existence theorem now, remains to prove, which we will do it in the next class, and then we will do the Green's function identity, Green's function, introduction of the Green's function, even in the context of a ball. Okay. Thank you. So, we will continue in the next lecture.